So lower bounds are really important. So this is the part that I actually get excited about. I know it seems like I'm always excited and speaking quickly, but this normally, like asymptotic notation, is not that thrilling. It's handy, it's really useful, but it's not sort of my favorite topic. Lower bounds are super cool. So I'm going to give you an example of a problem. This is actually the first problem a bunch of us in my third year, this was a problem we were given in my third year algorithms course when I was a student, and a bunch of us managed to figure out a tight bound for it. And we were super excited because we really felt it should be possible to do better than we were doing. And then we managed to show that no, we actually couldn't. Because we were really frustrated. So let's suppose that I give you a matrix. Well, I give you a scratch card, and it has it's a square matrix. 1, 2, 3, 4, 5. Okay. And I tell you that in here are, so it's one of these scratch cards. It's covered in this silvery stuff. So every cell in the matrix contains, so it's n by n. Did I hit the record button? Yes. It's n by n. I tell you that every cell contains a number between 1 and n squared. And every row is sorted and every column is sorted. Okay? And now I have a hat. It has all the numbers between 1 and n squared. You're going to pick a number out, and then you have to either find the number in the matrix by scratching off the cells, or you have to prove to me that it's not there. Not all the numbers have to be there. It just has to, like the numbers that are present in the matrix can be a subset, because some numbers can be repeated and some numbers can be completely absent. 6 by 5, wait, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay, oops. Yeah, got that wrong. Okay, so how many cells do you have to scratch off in order to either find the number you want, the number you drew out of the hat? Yes, it's in the notes. So you draw the number out. Well, imagine that you reach into the hat and you pull out a 1. Okay? Either it's here or it's not there at all. Okay? So if you're super lucky and you reach into the hat and you pull out a 1, or you pull out an n squared is either here or it's absent, then in the best case you pull out a 1. And in the best case it takes you at most 1 and at least 1. So in the best case, how many cells do you have to scratch? Theta of 1, right? Actually exactly 1. Usually we don't worry so much about the best case, but I am going to talk about it in the next class when we do sorting. So, what is the worst case? Okay, so now I'm going to show you that even when we're talking about the worst case, we want to talk about at least, right? Because we don't just want to say, I can say, well, it's going to take you at most n squared. And even if I tell you that it's going to take you like at most n log n, at most n, you don't just care about that. You want to know, yeah, but is my answer really the best you can do? And to say my answer is really about the best I can do, you need to be able to say you need at least about as many, you need to scratch at least about as many cells as I'm scratching. Okay. So, can somebody tell me an upper bound for this problem? I need at most, just write it in the chat. I need at most some function of n to be able to find that, either find my number or to show us something. Yes, I need at most n squared. Somebody wrote n squared. Because if I scratch off everything, then I'm either going to find it or I'm going to be able to prove it's not there. So this problem, there is an upper bound of n squared. Okay? Can anybody give me, can we do better than that? Can we do O of n log n? Can anybody tell me an algorithm? Yeah, you can do it because every row is sorted, and every column is sorted as well. So you start and you just do binary search on every row. It's going to take you n log n in each row, and if there are n rows, so it's going to be O of n log n. Okay, so actually we have, in the worst case, it's still going to take big omega, big omega of 1, because you're definitely going to have to, it's going to take at least 1. You're going to have to scratch something off, because you have to prove to me that, you know, either the numbers, in the worst case, it's still going to take you at least 1. So notice these aren't tight. We have this big gap at the moment. Gap. Okay, master theorem is happening on Wednesday. So, can anybody see something a bit better? For the interest of time, I'm going to tell you what the tight bound is. So, what you can do is, say you're looking for x. I'm so tempted to write that as just r with no apostrophe, but okay. So what you can do is start here and walk along until you get to something that's greater than x. And then, so let's say you're looking for x equals 15. Okay? So let's suppose that, so you walk along until you get to, okay, suppose that here, this is 13, and then you get to 16. And you're like, oh, okay. So now you found sort of this line, because everything below a certain line has to be bigger than x, greater than or equal to. Well, let's say bigger than x. Everything above the line has to be smaller. And so you're like, ooh, well, okay, so maybe this is 12. So this is 3, 5, 6, 10, 12. And then you say, okay, so maybe this is 19. And then you find out, like, this is, okay, this is 13 again. And then this is 11, and this is 20, and this is 18, and this is 12, and 14, and 23. Something like that. And we don't even really care about these because we never need to look at these because the rows and columns are sorted. Oh, yeah, okay. So you don't need to look at these. You just sort of walk down and you trace this line. Okay. So if x is going to be here, it's got to be on the line. Okay? How long does this take you? It takes you, well, walking across and then sort of tracing this line. How long is the line? It's n. So this takes O of n. You can do it in linear time. But now there's something, this problem, so actually maybe this is what somebody meant when they said binary search. It feels like what you can do, you have the matrix, and you look at the middle element of the matrix. Okay, so if you're looking for x equals 15, and this is 20, then you know that you don't have to look anywhere here. So you've just wiped out a quarter of the matrix. Okay? On the other hand, if this is 10, then you've wiped out the top left quadrant instead of the bottom right quadrant. Okay. So it feels like you could get something like binary search, but a two-dimensional kind of binary search, right? Does anyone, I could click this button that says poll. I could ask people if they think this sounds plausible. Yes, it totally makes sense. We were convinced, but the problem is, it doesn't, like you try and you're like, yeah, okay. So then we know we're up here, and then where do you look? Well, so if you're lucky, you look here, and maybe this is still 17, then you wipe this out. But that doesn't shrink it as much anymore, right? Because this shrank it by a quarter, and this is not a quarter of everything remaining. So, and then because it's like you have to recurse because this part doesn't relate. It's really frustrating because it feels like it should be easy. And then you keep trying it and it's not easy. And then you just feel stupid. And you wonder if it's just you or you need your favorite shoes and a coffee. And you think about it and think about it, and it really bugs you. And then you realize that this is why the lower bound is so nice. Because the lower bound, if you think about this argument, it feels like you should be able to do it in polylogarithmic time, like log n or log square n or something. But if you imagine somebody gives you the matrix and these are all ones. These are all fours. And on this line are all threes, maybe. Except maybe they're all threes, or maybe one of them is a 2. And you're looking for, well, I should have done this with 5, with 15, but let's say you're looking for x equals 2. You have to check the whole diagonal. If you don't check one cell on the diagonal, maybe that's where the 2 is. So these are all sorted, right? Every row is sorted, every column is sorted. And if these are all threes, you have to look at every 3 to know that none of the 3s are a 2. So how many cells are there on the diagonal? N. So that's where we get this lower bound that says you have, in the worst case, not in the best case, but in the worst case, you have to check big omega of n. And then we have big O of n and big omega of n, and how many cells do you have to check in the worst case? Theta of n. This is now a tight bound. You can stop kicking yourself about trying to get the two-dimensional binary search to work, because it's not going to. So this is when you get to go, now maybe somebody like messes around and gets something that works better on average, fine. Maybe they're a constant factor better, maybe instead of walking across, maybe they use binary search to find this red line. Maybe, but still, in the worst case, they're not going to be more than a constant factor faster. So we have a tight bound, and nudge. So, and notice that I was talking about the worst case, and I was using big omega. Big omega is a lower bound. So now I have, it's not best case, worst case. It's completely orthogonal to best case and worst case. So now we have this tight bound, and we all get to relax, because now we know that this problem takes a linear number of, you need to probe a linear number of cells in the worst case. And so there's this satisfaction of having a tight bound, that nobody is ever going to get something that's much, much better than we've just got, okay? And we have 12 minutes. I could sort of teach the master theorem in 12 minutes. Yeah, because, you know, master theorem is probably also on Khan Academy. So, it's also in the lecture notes. So this way, any questions about this stuff so far? And does anybody want to tell me, where do people get, Okay, so you can also talk about average case. But if you're very unlucky, you would have a matrix like this, you would reach in the hat and you would pull out a 2. So usually we're just going to care about worst case. Although in the next class we are going to talk about expected case of quicksort and quick select. But yeah, you have expected on average, probable with high probability, all kinds of. But usually people care about worst case. Well, theorists care about worst case, and practitioners care about real life. It's very hard to talk about real life, theoretically. Okay. 10 minutes for the master theorem. Okay, so now that we know what big O, big omega, and big theta mean, we can actually read the master theorem. So it's in the textbook, which isn't actually our textbook, it's the optional textbook because it's expensive, and I don't use it that much. So, but I need to just check what the master theorem says. And I need to fix that thing about the missing quantifier. Oh yeah, and I have also this note about Stirling's formula, Stirling's formula has a big O in it, and it's saying that's not the worst case. In what sense is it bad? Okay, so I have, yeah, this is long. Okay, so so this is kind of cool. You remember I said that that Appel and Haken, the 4-color theorem. Haken got his daughter to check the proof, check a load of cases. I mean, they got the computer to check the actual case, but Dorothea Haken, and then she got married, Dorothea Blessing, and she was my 3rd-year algorithms professor. Her PhD was actually the master theorem. So it was Cedric, I forget who, but there were like 3 authors, and I think she was the middle one. It'd be good to be constant. Let f of n be a function. And so this is for solving t of n be a recurrence. Defined on the non-negative integers. such that t of n equals a t n over b plus f of n, where we interpret, okay, where n over b could be floor n over b or ceiling n over b. That's ceiling. Okay. So there are three cases. If f of n equals big O of n to the log base b of a minus epsilon for some positive constant epsilon, then t of n equals theta n, no, yeah, to the log base b of a. If f of n equals theta n to the log base b of a, then t of n equals theta n to the log base b of a log n. I should just mention here that in the textbook, this is LG. I'm writing it log because it's standard. Once you're inside asymptotic notation, changing the base of the logarithm only changes a constant coefficient, right? Like if you go from log base 10 to log base 2, it just multiplies it by log 2 over 10. Yeah. Log 2 over log 10. Right, so switching bases, as long as you don't go to base 1 or base less than 1, which doesn't make any sense, usually, then it doesn't matter, and the constant coefficient is hidden in the asymptotic notation anyway. I just want to say this last part, and then I want to say what the intuition is. If blah 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 equals omega, this is not the strongest version. Last year I put something about this cannot handle all recurrences, obviously. It just handles a lot of recurrences that come up in divide and conquer. It doesn't handle, for example, the stuff that we saw on coloring graphs. But this is usually what you get in like third-year algorithms. You get divide and conquers that do this. So Karatsuba, it's in the lecture notes, Karatsuba, Strassen, merge or quicksort, blah blah, is omega n to the log base b of a plus epsilon for some positive constant epsilon, then t of n equals, oh yeah, there's a load of other stuff, rats. I'm not going to write all of that. So, and blah, blah, blah. There are a bunch of conditions here. Then t of n equals theta. So I have about 4 minutes left, 3 minutes left. And I just want to say, you can practice this and see this, but I want to say sort of what the intuition is. Okay? So if you think of your divide and conquer, you're subdividing the problem. At the root, you have the problem. There are notes. There is stuff in chat. Okay, inside asymptotic notation, the base of the logarithm doesn't matter. Okay. And so it's traditional just to write log. It does matter when you're in an exponent. But as long as it's down here on the base, then here it could be log base 2, log base 3, log base 10, it doesn't matter. Natural log, whatever. Because it's in the exponent, it does make a difference, because then a constant coefficient in the exponent is important. Okay, if you think of a tree, right? So you start at the root of the tree and with the problem, and you cut it into some number. So this is saying I'm cutting it into like A sub-problems of size about n over b. So I'm cutting it into, and if you cut it into, so remember Strassen, you're cutting something into submatrices of size n over 2 by n over 2, but there are 2 matrices, 4 submatrices, and each of them are 8 submatrices, but then you're actually doing 7 multiplications. So A and B don't have to be the same. So I'm cutting it into subproblems. And so subproblems of a size about a beef, the size of the original problem, and then I'm cutting into A of them. Okay, so you think of this as a tree where your branching factor is about A. Okay? And the cost of sort of cutting things into subproblems, and then you recurse. And so doing the cutting, doing the subdividing, and then later when you get these sub-solutions, you have to glue them back into a solution of the whole problem. That's taking you time f of n. Okay? So now, this is saying this is in the election notes, right? Oh yeah, so this is the case where you're chopping a lot and the sub-problems are, okay, 1 minute, okay. In this case, the weight is at the leaves, okay? Most of the work in this tree is going to happen at the leaves because you're subdividing fast enough that the work is down at the bottom because the tree is getting fat. Okay, it's getting, like there are a lot of leaves, the work is down at the leaves. In this case, it turns out that you're subdividing at about the same problem, at about the same speed that the problems are shrinking. In this case, you're doing about the same amount of work at every level. So if you've seen merge sort, right? In merge sort, you're doing linear work on lists which are shrinking, but at each level, if you sum up the total length of the lists, it's n. So the work you're doing at each level of recursion in merge sort is about theta n, right? So you're doing about the same work at each level of this recursion. How many levels are there going to be? There's going to be like log base b of a, and that's why. Okay, so I got something wrong there. But you're doing, so you get this extra log n factor. Okay. Oh, these are constants, so it doesn't matter. Okay. And then the other case, this last case, and then we're done. I'm sorry, I'm over time. This last case is when the subdividing and the joining the subsolutions together, that's really expensive, right? So you're chopping it into pieces, but then each of the, so for example, if it takes you time 2 to the n to do the subdivision, then and you chop it into like 5 parts, then it's so much easier to deal with the subproblems than to deal with the main problem, that then what dominates is the f of n. So in this case, it's the leaves that are important. In this case, it's sort of every level is equally important. And in this case, it's the root that's important. And I just wanted to say that because that I find people tend not to get if they check other sources about. But you can find out about the master theorem. This is all in the lecture notes anyway. Might have some typos and I might have got some stuff backwards, but like I said, nobody gets this perfect all the time. Okay, sorry, I'm 2.5 minutes over time. Lecture stops. Have a good day. It's a beautiful day outside, at least in the